Okay, today I'm going to talk about the reducing drag conflictation of an armored body using the ANSYS fluid. Okay, there are five members in our group. Our lecturer name is Muhammad Farooq bin Abdul Latif. The first one is myself, Harina Analaki Kautaman. The second is Yoga Analaki Marimuthu. The third one is Mahadevan Analaki Sugumaran. Fourth one is Sarve Analaki Marimuthu. The last one is Savinash Analaki Mohan. Okay, the learning outcomes and objective is the first one is about the objective, reducing the drag conflict of an armored body using the ANSYS fluent. The second point is analyze the aerobatic performance through the CDF simulations. The key task has been for the armored body is model setup in the CATIA V5 and HyperMesh. Second one is simulation with the ANSYS Fluent 2 million and 1.5 mass. There are two models, is a 1.5 mass and 2 million. Compare the baseline with a 19 degree of flanks and modify the 90 slanks of model.
Good afternoon. My name is Yogan, son of T. Marimuthu, and now let's look at the introduction to hammered body. First, simplified car model for aerodynamic research. Second, dimension, which is 1044 mm length times by 288 mm height times by 389 mm width. Third is focus, which is rear slant angles impact on drag and flow separation. And the fourth, why, mimics real world vehicle airflow patterns. Okay, now let's look at the problem statement, which is need to reduce drag using simulation. Second, no physical prototype. Third is importance of balancing drag and down force. Okay, now let's look at the literature review condensed, which is Hammett et al. 1984 baseline for slant angle studies. Second is Spoon and Gillerian, which is water tunnel flow behavior. Third is Tau ATL 2024 DEs versus RAND's model. And the fourth is summary. Many studies point to slant angle as key drag influence.
Hello, my name is Sharin Alanaki Marimuthu. So I will be continue presenting about the model setup. So we use Katia V5 for the geometry modification and Hypermesh for mesh and boundary condition. We also use ANSYS Fluent for SST KW and 13.198 ms inlet velocity and pressure outlet. So for the methodology, first for the model setup, the baseline is 19 degrees slant angle. So for the modified version, we use it's a 90 degree slant angle. It's plus 150 radius adjustment. The simulation setup is meshing in hypermesh. So the boundary condition is inlet velocity 13.98 millimeter per second. The turbulence model is SST K omega, and the analysis is drag coefficient CD, pressure distribution, velocity, and turbulence. Results that we get from the drag coefficient from the comparisons. So for the model version, the result for CD is 2 million mesh and 1.5 million mesh. So the baseline we got 0.180 compared to the 0.180 for the 1.5 million mesh and 0.180 for the 2 million mesh. The 90 degree slant we got 0.064, and the 1.5 million mesh we got 0.0671. So the key insight from here is the 90 degrees slant reduced drag by negative 63% vs the baseline.
This is the result of the pressure and velocity. The pressure coefficient is baseline is minimum 3.66 and maximum 1.05, and 90 degrees slant minimum equals to negative 2.38 and maximum 1.08. The velocity magnitude is 90 degrees slant, more uniform flow maximum to 3.59 versus 51.8 is based in baseline. Conclusion: smoother pressure distribution and reduced turbulence. This is the flow visualization. Baseline model with high turbulence, and then second is 90 degrees length model with control flow separation, and reduce the wake size and vortice in the modified design. This is the discussion. Why 90 degrees length perform better? Because delay flow separation, minimize low pressure zones at the rear, and lower turbulence kinetic energy 0.035 meter square per second square versus 3 to 5.68 meter square per second square in baseline. Practical impact is improved fuel efficiency and vehicle stability.
Challenges and limitation. Matching sensitivity 2 million versus 1.5 million. Result varies slightly. Simplified model ignore underbody real world complexities. Time constraint limited advanced optimization. Comparison matrix. Number of elements is 1.5 million. Drag coefficient, also known as CD, is 0.18, and pressure coefficient, maximum pressure coefficient will be 1.05, minimum CP will be 3.66, and velocity magnitude will be 5.18. Therefore, for 2 million, number of CD will be 0.18, pressure coefficient will be, maximum pressure coefficient will be 1.07, minimum coefficient will be 2.78, and velocity magnitude will be 5.5. Below they have shown the scaled residual for both of the elements. Conclusion and future work. Conclusion: 90% slant angle significantly reduce drag. CD equals to 0.064. Validated ANSYS fluid for aerometric optimization. Wherefore the future work test intermediate slant angle, example 25 to 40 degree. Incorporate experimental validation while tunnel. Thank you for watching on behalf of myself and also my team.